Okay, I think we'll get started. Hello, everyone. Maybe I don't have to use the mic. Can you hear me in the back? Good acoustics. This is great. Right. Hi, I do. For stream, yes. Sorry, people watching online. I apologize. My name is Yaron Schneider, core maintainer of the Dapper project, steering committee member, also CTO co-founder at Diagrid, and together with me we have Roberto.
Yes, my name is Roberto Rodriguez. I'm also a new Dapper maintainer, creator of the Dapper Agents project, and I'm also part of the NVIDIA team. So I'm going to be doing how to enable autonomy, how to enable AI agents into security operations to defend NVIDIA's products.
Okay, I'm going to take the first section of our talk. Let's start with community updates. The Dapper project has been through a lot. It's gained new contributors, new end users, and one of the most important things that we've seen during the last year is that now we're a graduated CNCF project since November 12, 2024. And this is really a testament to the validity of the project, its broad user adoption, the number of contributors that are contributing to the project. And it's been a journey to get there, but if you ever contributed to Dapper, opened an issue, communicated with maintainers, you have our thanks. Beyond this, we are one of the fastest growing projects in CNCF, currently 14th largest, over 700,000 Docker hub pulls a month, more than 300,000 unique doc views, and our Discord community recently surpassed 8,000 members, and we're closing up on 4,000 individual contributors. This is great, and beyond all that, the most important thing for us is to actually measure end user adoption. So this has been pretty much off the charts. The Python SDK grew 151%, I believe, year over year, which is very much fueled by AI workloads that we'll talk about in a second. .NET continues to see almost, I think it's actually over 200,000 downloads per week now, which is pretty great. And of course, we have other languages using Dapper, but we don't have great ways to track them. This is obviously public metrics that we're taking. We're seeing amazing use cases. This is my own personal favorite, NASA running Dapper on the International Space Station. What it's doing there is Dapper is being used as the message bus layer to take pictures of astronaut suits and then fire those off to a machine learning model that decides if the suit needs fixing. In this case, we can see the glove. So essentially check for tear and wear. This is the ultimate edge deployment in our opinion. All the way to companies like Grafana that built their secure supply chain on top of Dapper on AWS using Grafana Cloud. This is essentially the basis for their entire infrastructure stack, scanning container images for CVEs. And there's many more. We've released dozens of these case studies. These are just two that I particularly like. Recently, we've released Dapper 115, a really important release because it saw some pretty interesting additions and also improvements to the Dapper project. We've added Conversation API, which is a way for developers to securely and reliably talk to underlying LLMs. And of course, this isn't just a pass-through. Essentially, when your application talks to any of these models using Dapper, you can apply circuit breakers and retries and timeouts, and you can kick authentication middleware. You can do authorization, all before talking to the actual LLM. And on top of that, we add enterprise features like sensitive data obfuscation, which means if you want to make sure that the user prompt, which can really be anything, doesn't contain any sort of personal information like credit card numbers, social security numbers, names, emails, Dapper will do that for you. And that's a very hard problem to solve. Also, we can obfuscate data coming out of the LLM. So if you have your own personally trained model and you're afraid you might have put some data that shouldn't be there, Dapper can actually make sure that we obfuscate that data going out. And then prompt caching, which is great. A lot of LLM providers do have prompt caching, but with that prompt caching, you still need to send the request out of your cluster. So you still need to pay for network charges when hitting those. And even if you hit the cache, you will still pay about 50% of the charge for that cloud provider. With Dapper, all of that is gone. You don't need to do that anymore. All of the caches are actually saved in the Dapper sidecar locally. Latency is extremely low because nothing ever leaves your cluster, not even your VPC. So this conversation API is new and it's garnered a lot of attention. We've released with these providers that you can see here. But ever since we've released, we actually had community contributions to add Google Gemini and Olama to Dapper. So come 116, at least these models will also be introduced. Our community is very enthusiastic about adding them. Workflows has now become stable. Workflows has certainly been the most interesting building block for developers since we first announced it in Dapr 1.12. There's many large companies that took it to production, even though we told them not to take it into production, which is interesting, just because of the value adds that it provides. Now it's production ready, so now you can take it into production. If you're watching and you did take it into production and you're having issues, then these issues should be gone now. If you're still having issues, please come talk to us. The maintainers, we like to fix things. So please, if you find workflows interesting, if you didn't use workflows up until now because it wasn't stable, please go ahead and take them out for a spin. We support Java, Python, Go, C#, JavaScript, TypeScript, and PHP is coming. We have a community contributor who's creating a PHP SDK for workflows. It's going to be really interesting to see how the web meets these durable workflows, and we're going to cover them more soon. It's now ready for pretty much anything you want to do. The programming model is so general purpose, you can essentially use it to do anything from data processing to notifications to timers and reminders to even writing your own Kubernetes-like server, and also AI agentic systems, which we will cover more in this talk. So what do workflows allow you to do? It allows you to create very complex distributed systems pattern in a very easy way. So task chaining, for example, is where you have one activity that's followed by the other, that's followed by others, and we take the input from one and we feed it back again. One example that I like to use is a morning routine. Actually used it yesterday, so I really like using it. And you essentially wake up, you hit the shower, you brush your teeth, and then you go make your coffee. If, for example, you couldn't make your coffee, you don't want to need to go all the way back to the shower. This is essentially the guarantee that Dapr gives you. You can fire off tens of thousands of those activities. Dapr has a very smart, efficient event sourcing mechanism, which allows it to track the state of each individual activity. It'll know where it needs to pick off again, and it will continue the execution from essentially where it left off. Fan in, fan out, that's your standard MapReduce-like pattern. You can fire off, again, tens of thousands of these in parallel. So imagine you're firing 1,000 batch jobs with Dapr, and one fails and 999 succeeds. Dapr will actually track the state for each and every one of those, and it'll make sure that only the one that failed actually retries. So this can lower costs. If you have I/O operations, or you're hitting things like LLM providers, for example, which cause you to pay, Dapr will make sure that, well, that just doesn't happen, because it will not kick off, again, activities that actually ran to completion successfully. And then you can aggregate those results. The monitor pattern allows you to create durable timers. So it's something like, an alarm clock for applications. Remind me in 1 week, 1 year, Dapr, since 1.15 can actually slip to infinity. So you can have something that will just wait for years and years and then wake up, and it's allotted time, and hit your application, and this is durable. The cluster goes down, the database goes down, this thing will remain. So it's a pretty nice scheduling semantics for lots of applications. External system interaction. This is something extremely important, because this is essentially a human in the loop, or today, humans and AI agents in the loop, where your system needs to execute a workflow and then pause because it's waiting on an external event to come in. Something like a human approval. Someone needs to approve a form or an order that went through, or you want to give it off to an AI agent that's going to make a decision that's going to resume the workflow. So that approval event can actually come from any system. And again, Dapr can sleep for a long while and survive network interruptions, pod disruptions, complete shutdowns. And once the system gets back up and the approval is being forwarded to Dapr, the workflow will continue. So now let's switch gears and talk about how all of that relates to AI agents. The very basic concept of an agent is that it's autonomous, and this is why they're actually useful. You have a user here. Now, these users, granted, they can be processes, they can be other agents. In this case, it's a user, and we issue a prompt into the agent, and then the agent kicks off a workflow. We essentially reason about what we want to do, or what the agent wants to do, because it's not really us, and then it plans. Then that plan goes into an execution phase, which is called action. And to be able to deliver the best action, the agent needs to choose the correct tool that is best for the job. Then it will essentially fire that off and observe the result, feed it back to the LLM, send it back to the user, and hopefully everything executed to completion successfully. And those tools can interact with anything. It can be your internal systems. It can be external systems. It can be pretty much systems that even give you a dynamic list of tools while the execution is going, so you don't necessarily know in advance which tool you're going to be kicking off. And so these workflows are extremely important, but workflows, as we've come to know them since pretty much software has existed, are very different from agentic workflows, because regular workflows are structured. They are predefined, predetermined steps. We essentially code stuff, and we know how the code's going to work. We expect that if we launch the same code again, we're going to get the same result, because otherwise it would have been insanity, Einstein said. So this rule-based orchestration doesn't have real-time adaptation. Yes, parameters can change, the data can change, but the workflow remains the same. The number of steps remains the same. The tools that you use in hard code into your workflow, they remain the same. It's repeatable and it's structured, and this is what we've been spending the last 40 years writing software for. Software that makes these structured executions reliable and secure. But now, everything's a little bit flipping on its head, because agentic workflows are not that anymore. Imagine your brain, as a developer, was connected to the code you write, and you were examining the execution state and the input-output state at any given stage, and then making decisions based on what it is, decisions that are not hard-coded. So Agentic AI is essentially like that. It'll take it blends workflows, structured workflows, with AI decision-driven making, which means that it can make a choice about what activity to run next, and that might not be the execution that it ran last. This thing is highly unpredictable. It uses reasoning, which we don't fully understand, to dynamically choose the best path based on the incoming data. And all that needs to enable autonomy, because agents are only really useful if they're autonomous. But the more autonomy they have, the more things can go wrong, because the more autonomy we give them, the more choices they have, the more choices, the more permutations of different situations and activities that can occur. And so this becomes a problem because, as I said, we've been writing software to deal with structured execution, and now we need to deal with something completely different, which is adaptive and intelligent. And one of the main things about agents is that it's not really hitting production systems yet, but it will soon. And when you take them into production, you're going to be running into issues, keeping those things reliable, making sure that if you have 200 operations now that the AI agent essentially kicked off, that they all complete in the time that they need to complete it by, or that they retry based on where it left off, because your workflow might be dynamic in nature. It might not be idempotent. You might need things like exactly once executions of these systems, and the more responsibilities you assign to it, the more can go wrong. So having a very resilient foundation and infrastructure to these AI agents is crucial. And if we look at a lot of AI agent frameworks out there today, they're great for demos, great for POCs. Of course, I'm not going to name any names, but it's good to get things going. But they don't have the same level of durability and resiliency that Dapr has with workflows. So how do we combine these two things? How do we combine these easy interfaces for developers to write AI agents with these durable workflows that Dapr has in a way that is adaptive to things that are dynamically changing? There's other top challenges here, except for reliability, which we've talked about, because again, with reliability, the chances of failure increases with the level of autonomy. Security is another one. How do we encrypt communication between agents? If you think about agents, they're like the perfect microservices, right? Every developer tries to decide how to best model their application and encapsulate their business logic. And we want to do domain-driven design, where we encapsulate all of our domain into a single class or a bunch of classes or a service. And every time something bleeds through the interface, this will never, ever stop. But with agents, it's actually pretty easy to arrive at architectures that really make them reusable and repeatable. So you can think about having many agents, each one doing its own task, and then an orchestrator agent that picks the best agent for the job. And these agents can dynamically scale up and down instead of running a monolith agent, which is going to be extremely problematic, especially as it becomes a single point of failure. If you've got many different scenarios to run with a single agent, if the agent essentially fails, then all of the underlying activities, all of the underlying executions, well, they're not kicking off anymore. It's a very problematic, noisy neighbor problem. So how do we actually encrypt these agent-agent communications because we want to have multiple agents, each bounded to their own context. How do we do authentication between agents? That's a problem. They don't necessarily adhere to, standard protocols. How do you authorize these agent-to-agent communications? And of course, cost efficiency. We all want to be very much aware of the costs it takes to run our software. And these agents can become very, very expensive to run in terms of CPU and memory consumption. In the Dapr project, we have come up with a project that we announced recently called Dapr Agents, and it is essentially a solution to answer all of those needs. It's an agentic framework built on top of Dapr workflows. It is a unified programming model with Dapr. You can use all of the Dapr APIs with it. It facilitates multi-agent collaboration. It allows for authentication, authorization. All of the Dapr APIs and building blocks that you use for resiliency can be applied to these agents. And you can also run thousands of agents on a single core because this agent framework is built on Dapr workflows. And Dapr Workflows itself is built on a concept in Dapr called actors, which is a very, very lightweight process that encapsulates its computing state. And Dapr can essentially move millions of those within even a 5-pod Kubernetes cluster with 4 cores. And so we talked before also about workflows and full autonomy versus deterministic. Well, with Dapr agents, you don't have to give up one architecture for the other. You can actually choose whether you want to allow the agent to fully autonomously handle the task, or if you want to write your own type of workflow manually and then connect it to a task that is autonomous using a different agent. But Dapr will guarantee durability all the same. It doesn't matter if you're giving the agent full autonomy. Dapr will make sure that even if you connect it to thousands of tasks, each one of these tasks will essentially be a durable activity that finishes and picks up where it left off, even in the face of the most catastrophic failures you can think of to your underlying infrastructure. And to talk to us more about Dapr Agents, I'm going to let the original author of it, who contributed it to the Dapr project, Roberto, take us forward. Thank you.
All right, thank you very much. Yep. All right, so let's go to the next one, I guess. But so before, I guess, we start talking about this, the Dapr Agents project, it was something that first I wanted to figure out how to build my own agent. So as a security researcher, I wanted just to learn and kind of like reinvent the wheel a little bit just to learn how every component was working together. But at the same time, as part of research, I wanted to figure out what was out there that I could use, right, built on the top of something that has been proven to work in production. And that's how I got to Dapr and the whole ecosystem. So when you start thinking about agents, there is multiple components of an agent, right? You have the concept of memory, the concept of tools, state, how they communicate, once again, how they plan. How do you save the plan and then distribute that plan across all the other agents that are part of your multi-agent collaboration system, right? So there is a lot of things that we have to consider every time we start thinking about agents. Now, when you think about the workflow concepts, there is actually this is known as an agentic pattern, right? So instead of saying agentic workflows, in the community, in the AI community, I guess, it's an agentic pattern. And there was this one that came out in, this one was in October 2022. This was actually before ChatGPT, which was November 2022. And this was kind of showing that we do not just have to talk to an LLM and get facts all the time in this iterative loop, right? Can we actually make a system to interact with the outside world? So this agentic pattern was proposed in this paper. So you have to make it think, so have the language model think about your question, figure out how to act in the real world through tools. This could be applications, functions such as Python function, for example, and then try to get that observation so that then you can make the language model try to figure out, do I have to continue this loop? Do I pick the next tool? Or maybe I'm ready to answer the question. That was a basic agentic pattern. But when you start thinking about this pattern, this is a basic workflow, right? This is a set of sequential or just multiple steps that you can run one after the other one, trying to get the output of the first one, the second one, third one, so on. And then at the end, you create this loop where the language model is the one that is going to reason. And once again, it can continue the loop or it can stop the loop. So this is something that, in my opinion, in the community, in my opinion, we were not thinking about this just as a workflow that we can simply define how we're going to execute all of this. Now, this took us to multiple different agentic patterns where you can have your basic loop where you execute something, you can critique that input, and then you can just go back until you feel comfortable, or maybe you say, I want you to critique this output like 10 times, right? You can also add planning, so you can add a step where you want to make sure that you define initial steps and then go through the whole loop again. The most known, of course, at the bottom left is the tool calling. Tool calling means that I just want to know what tool is the best tool to choose to execute for each iteration. And that could be combined with the critique. It can be combined with the planning before you start that flow or agentic pattern. And then at the end, the one that is super interesting is, can you have all of these agentic patterns as, let's say, microservices, and then have all of them communicate, where you can define the tools for each service. You could say you're going to be, for example, as a security researcher, you're going to be the threat intelligence analyst, you're going to be the reverse engineer, the incident responder, the security analyst. You can provide multiple tools, and you can have them all communicate right with each other. Of course, when you start thinking about these patterns, once again, this is what we all see in the community, but you can use the fundamentals, task chaining, fan out, fan in, all the way to monitor, right? You can mix them up, and you're going to start building your own agentic patterns. That, of course, caught my attention. And when I found out about Dapr workflows and all these different patterns, I was like, this is the tool that I need to use to start building my own agentic, workflow, engine, right? And of course, Dapr workflow has the durable task, concept, which Yaron already explained a little bit. So it was very interesting to try to define my workflows or my agentic patterns in a easy, programming-friendly type of mode, as if I was writing just a Python script and try to figure out how all of these tasks or activities were connected, right? So when you start thinking about Dapr workflows, right, for those that have used Dapr workflows, on the left, you can see what it would look like if you just want to directly use the concept of a workflow, the concept of an activity, and then define maybe a client to interact with, these providers for language models. In the concept of Dapr agents, we come up with the concept of a task. And a task is a wrapper around the activity where you can define, I want to run this task with this LLM provider or this specific language model. And if you can use the concept of a Python function, right, using docstrings, using a decorator, so it is easy to say, I want to run this task. The description of the task is going to be this. And then Dapr agents will take it as this is going to be an LLM-based task. Let's take the description of the task as a prompt, and let's execute it with an LLM. That's the fundamentals of trying to use these concepts, create this abstraction layer where you can define LLM-based tasks. Now, of course, the beauty of this is that every single agent that you build, right, is connected to multiple components that if you run, for example, this locally, you already have access to multiple things that you can use through, right, testing, such as, Zipkin, Redis, to kind of keep the state of the agent, all the way to, of course, the whole ecosystem of Dapr, which was something that, to me, I don't have to rewrite. Once again, I love to reinvent the wheel to learn, but my main learning thing was I want to learn how agents work, not so much how to build all the architecture and all the services and all the standard APIs that I could use to communicate with multiple things, right? So that was kind of like the thought process. Of course, just having durable tasks is not enough. We want these systems to communicate, right? Because we want to make sure that each one has its own personality, its own role, its own tools, its own goals, for example. And for that, we use the pops up APIs. There's a lot of conversations on creating even standards into how to make these agents to communicate. Well, there is cloud events already, which is a standard that we could use, and it's pretty good at tracking more metadata than the things sometimes that I see multiple frameworks trying to track when they communicate. So this is just an example of how we can have agents simply using that API and try to exchange messages. The other concept, of course, which was amazing, right, is that I don't want to think about on building multiple clients and modules to interact with multiple architectures out there. So trying to make it agnostic to all of this was amazing, right, because there is multiple components that you need as core components of an agent that it would be great just to swap, right, if I'm working in different environments. So the previous example, think about this, that I don't have to change the logic of how they communicate. I can simply swap the main component. In this case, if I like to use Redis, great. If somebody else wants to use other components in here, that's also possible just by swapping the right components. And then at the end, we try to mix other concepts of Dapper. In this case, every single agent must have its own state. And the way how it works, this is very basic example, is that when you interact with multiple agents, one approach is to say, I want everyone to know what's happening at the same time, everyone. So if the one on the left, the green one, is the orchestrator will send a plan to everybody. It's going to send messages to everybody. And then the orchestrator could say, now you go next. So he can point to a specific agent, and now the agent has all the previous messages, the history of like what's going on. And every time the agent stops, right, finishes the execution of the task, it can broadcast that message so everybody is aware of what's going on. So trying to keep the communication through PubSub and also use the state APIs, super powerful to start building all these agentic systems. And let's go to the demo, which I guess first, the demo is going to be, we're going to use this basic agentic pattern, which is, let's say the whole pattern, which is the concept of an orchestrator and then assistants, okay? So how does that work? The orchestrator is going to get the main task. It's going to generate the plan. It's going to send the plan. It's going to then trigger agents, and agents are going to send a response back to the orchestrator, and that will be broadcasted to everybody else. The orchestrator is going to figure out if we can pick another agent to execute the next step, or maybe we're good to go, and we just respond back to the user, right? I want you to think about this as a workflow for each microservice, each component of this whole ecosystem. The orchestrator is going to take the task, as I mentioned before, and you can take the purple, let's say rectangles, as the tasks, right? And then you can see that once it gets to the checking the progress, it's going to decide. The model behind the orchestrator is going to say, based on the input, based on the current messages in my state, I can continue. So we use the continue as new API, which is part of the monitoring right pattern from Dapper workflows, or we can simply stop and then talk to the user. Very simple pattern that where we are using multiple Dapper workflow patterns as well. This one is the assistant. All the assistant is doing is getting a message from someone, in this case the orchestrator. It's going to take the message, look at the state of what's going on. It's going to execute a task. And this assistant can suggest a tool to execute, or it can simply respond back to whoever sent the task. If it is about to suggest tools to execute, it's going to execute them either in parallel using the Dapper workflow, fan out, fan in patterns, right? Or it can execute one tool at a time depending on how the model decides to do it. And this is the whole flow back and forth into how this model, this agent is using the Dapper workflow tasks and also some APIs like the continuous new. How do you define an orchestrator? That's on the left, very simple. We already have some built-in classes that you can just define an orchestrator, provide the attributes, the name, how it communicates with the state stores, and then you can expose it as a service, for example, so that you can have someone sending a request to an HTTP endpoint, and that's how you would trigger the orchestrator. And the concept of an assistant, we also have the assistant class, where you can define the name, the goal, the role, the instructions, tools, etc. And we pack all of these workflows into these classes, so it's easy to allow you to describe all of this in a type of microservice way. And then, of course, we use concepts such as running multiple apps at the same time. So you can see how we have every single assistant, right, pointing to its own Python script with our own assistant classes. And at the end, we have our also workflow orchestrator, which is going to run the other workflow that has the decision of who speaks next and try to send the plan, etc. So let's run this real quick. The way how this works is, so let me just make sure I have this. Hopefully you can see it. But if you go to the GitHub repo, there is a quick stars, and there is the Dapr YAML files. Let me just make sure this one is easy to read. Maybe I'll do this. As I mentioned before, you can just explore every single application that it's in the folders. And if we go, for example, to the Dapper workflow LLM, this one, we can even change the max iterations. You could say, I want this to run for 10 iterations. And then we are ready to execute this. But before that, you could actually use the built-in Docker containers, I guess when you deploy it locally, where are going to keep track of your state. And they're also going to, we can see how all of these tasks are being executed. So let's run this. So we go to the folder where this exists. We're going to do Dapper run F, and we're going to run the Dapper LLM YAML. We're going to run this, and then we're going to make this one a little bigger. So this one right here is trying to as you can see, listening to the client. There is a client that we define in order to automatically trigger an event. In this case, the event was, let's take the ring to Mordor. I'm a big fan of Lord of the Rings. So all the microservices were our characters, like Gandalf as a wizard agent, the Hobbit, Frodo. And the orchestrator is just trying to figure out how to communicate with all of them. If we go to the...
and get the best plan for how to run or take the ring to Mordor.
Yes.
But we're all smarter than the LLM and the agent, because what's the easiest way to take the ring to Mordor?
Yes.
Yes, thank you. Right.
Exactly.
But the LLM's not going to tell us that.
So one thing that you can do, let's make sure I have this in here. So one thing that you can see automatically, we're using this state to first trying to keep track of what were the agents that actually are part of this whole ecosystem. That way everyone tracks of like who is available to actually speak. We can see, if we go back here, we can have the concept of a beacon channel, which the beacon channel pretty much what it does, let me make sure I zoom in here a little bit. So the beacon channel pretty much is saying everyone who is connected to this specific, let me just make sure this is bigger, to this specific topic. So you can see all the microservices are connected to it. So they're just waiting. If anybody broadcasts anything, I'm going to act on it, right? And all of these classes are listening on all of these topics, right? Now, as this is executing, right, it's kind of going through the whole loop one by one. We can probably talk a little bit about this, where you can see that there is broadcast messages being validated, etc. But one way to look at this is Dapper Agents provides a file that is going to be created for every single application that is being part of this whole agentic system. And we're going to keep track of like what's going on. And this is all structure output. And this is actually was created by the model. So let me just go straight to the first part. This is the concept of a plan, for example. Let me just make this a little bit bigger so you can see it. There is a concept of a plan. Where is the plan? Right here. Where it's saying, step number one, we need to assemble and prepare all the necessary supplies. The model itself says we need to have sub-steps. We need to make sure that we are provide more information into what needs to happen. And then this plan is being iterated over and over, being passed across all the agents. And as you can see, it's also some of them are completed already. So what does that mean? Every time we check progress, we assess the current state of everyone, we assess the plan and the question, and we start making the model to produce updates to the whole plan. And that's how we can say, we're completed, we're still in progress, we need to probably give it to another agent. And then as you can see at the bottom, if we scroll more down, we can see the task history. And in this case, what that means is every single agent, like Gandalf, Legolas, Gandalf again, all of them are tied to the tasks. So the model itself is a language model, is reading the output of all the services, is going through the whole iteration process, and is trying to figure out like who did it, right? Who actually was assigned the task. And you can see that it's going step by step, and this file is being updated in real time. One thing that is pretty interesting is that some tasks, and this was actually an interesting result, where the unpredictable happens. For example, some tasks were being completed, subtasks, without the actual agent completing it. And that's because the model was assessing that based on what these other agents did, these other tasks are already completed. So we have a prompt that says you need to validate if whatever information you have in the current state is going to support other operations. And all of that is happening autonomously, right? And then this one, I would assume it just finished because my output was NA before, but this was updated in real time. And this kind of tell you exactly what happened at the end, producing an structured report. And all of this is possible by having all of these systems communicating with each other, keeping the plan, the state across all of them using, in this case, a Redis local Docker container. And then you can have this output that then you can probably use it to validate how good this agent is at a specific task or not, which is what we do in security. We try to validate how close the report was to what a security analyst would do, for example, when they investigate an alert. Right? So having this structured output allows us to then take this and see how efficient it was or not. And that was it.
Yeah.
Yep.
So this is the end of our maintainer track. Please try out Dapr agents, join the Dapr Discord, talk to us, and we're happy to talk about whatever Dapr use cases you think you might have, or just anything else. So thank you so much for coming here. Thank you for your time. Thank you.
Thank you. Okay. Do you have questions? No questions. Okay.
And we're here for questions. We will remain here. Huh?
Questions like this?
I think they have a mic in there.
Yeah, question?
I think it's for the recording.
Oh, yeah.
Yeah?
One, two, three.
There you go. Yep.
Okay. Thanks for a great talk. Really good to see how AIs or agents are tackled from sort of a microservices perspective instead. That's great. I'm Morten Forfang from a consultancy in Norway. Anyway, I was just wondering, if the Dapr part takes care of the planning, that I'm the orchestrator and you guys get everybody gets the plan, right? But these are agents, so one of them might come up, raise their hand, and say, "I got a better plan. We should stay in Rivendell. We shouldn't actually go to Mordor." How does the approach possibly accommodate a more kind of a dynamic, the plan has changed kind of scenario? That was my question.
Yeah, it's going to be an iterative loop.
Yeah, exactly. So we keep the same concept of an iterative loop. In this pattern that we show, we have the orchestrator with the language model deciding what to do next, what not to do next, what updates actually need to happen. So there is already the orchestrator trying to figure out what's the best path based on the current state and the current tasks that are being completed. So that's kind of being taken care of already. But I also like your question when it comes to what if an agent just decides to update it, right? That's possible. And that's a pattern that we're working on, which is the swarm pattern, where all the agents themselves, based on their own tools, their own goals, their own roles, they could actually propose even changes to like what's going on across the whole ecosystem. So there is different patterns, same concept. You just move the reasoning of what's next to the agents versus having an orchestrator like a manager trying to send the tasks to everybody. And there is, of course, papers that talk about which one might be more efficient to specific use cases, right? So I think it depends on what you're trying to do. For us, trying to have one orchestrator with a reasoning model, those that are like, for example, like O1, O3 in OpenAI, for example, or DeepSeek, right? Like, reasoning models are great as orchestrators because they can reason a little bit more than maybe you just want your agents to be the typical, give me some input, I'll decide what to run, execute it, and I'll send you back the result. That's probably more efficient if you have hundreds of those trying to do things, and the orchestrator will be the one, sharing things. But good question. You can still push the reasoning to each agent. Yeah.
Any more questions?
Any more questions? We have the mic in here.
Okay, we have the mic. Yep.
No questions. All right.
All right, cool. Well, thank you.
Thank you very much again. Appreciate it.